Today, we are talking about something so small you can't see it, but it's so powerful that it's basically the gatekeeper inside every single microchip. You could say it's the engine of our digital world, and we're about to figure out exactly what it is.
So, let's just start with the question. What in the world does your smartphone have in common with a solar panel on someone's roof? I mean, they seem like they're from completely different universes, right? But deep down, at their very core, they run on the exact same physical principle.
And that principle, it's a tiny invisible barrier. The best way to think about it is like a microscopic, perfectly controlled one-way street just for electricity. It lets the current go through one way, but it absolutely slams the door shut if it tries to come back the other way.
This little piece of physics magic is called the P N Junction. And honestly, it's not an exaggeration to say it's the foundation of our entire modern world. So, how does this thing actually work?
All right, to get a handle on the P N junction, we first have to look at the two things it's made of. We start with plain old silicon, which is a semiconductor, and then we do something really cool. We add specific impurities to it to give it special powers. That whole process, it's called doping.
And this doping process creates two different, let's call them flavors of silicon, P-type and N-type. It's pretty simple. P is for positive and N is for negative. And the real genius is that by putting these two different types right next to each other, we suddenly get this incredible ability to control electricity.
Okay, so this table breaks it down perfectly. You see, for the P-type side, we add an element like boron. And what this does is create a little empty spot where an electron should be. Physicists call this a hole, and it acts just like a positive charge. Then, on the N-type side, we add something like phosphorus, which has an extra electron that's free to move around. So here's the big takeaway. In P-type silicon, the current is carried by these positive holes, and in N-type, it's carried by negative electrons.
So we've got our two pieces, our P-type and our N-type silicon. But the real magic, the thing that makes it all work, happens the moment you bring them together. Let's look at what happens right at that point of contact.
The instant these two materials touch, a totally natural process called diffusion kicks in. You know how the universe loves to find a balance, right? Well, the N side is sitting there with a massive surplus of free electrons, and the P side has a ton of empty holes just waiting to be filled.
So you can imagine what happens. Those extra electrons on the N side see all those empty holes on the P side, and they just rush across the border to fill them up. They combine, and poof, they neutralize each other right there at the junction. But this leaves something behind. Fixed charged atoms that can't move. Positive charges on the N side where electrons left from, and negative charges on the P side where they landed.
This process creates a brand new zone right at that interface, and it's called the depletion region. Why? Well, because it's been depleted of all the mobile charges. The free electrons and holes are gone. What's left is basically an insulating barrier with its own tiny built-in electric field. And this barrier, this is the gatekeeper we've been talking about.
So we've built our gatekeeper, but how do we actually use it? How do we tell it when to open and when to stay shut? Well, the answer is surprisingly simple. We just apply a little bit of electricity from the outside. This is a process we call biasing.
You see, by applying a small voltage across this junction, we can either push against that little built-in field to make the barrier shrink, or we can help it out and make the barrier even wider and stronger.
First up is what we call forward bias. This is how we open the gate. We connect the positive end of a battery to the P side and the negative end to the N side. This external push shoves the positive holes and the negative electrons right toward the junction. They basically steamroll that little internal barrier, making the depletion region super narrow. And just like that, current flows through easily. The gate is wide open.
But what happens if we flip the battery? That's called reverse bias. Now we're applying a negative voltage to the P side, and the total opposite happens. The external voltage yanks the holes and electrons away from the junction. This makes the depletion region get much, much wider, and the barrier becomes way higher. The gate is now slammed shut, and basically no current can get through at all.
And that's the whole point. This incredible one-way street behavior is the key. This ability to turn electricity flow from a two-way street into a one-way highway is called rectification, and it is one of the most important fundamental jobs in all of electronics.
So we have this incredibly precise, almost magical device. You'd think it must have been the result of years and years of careful, deliberate planning, right? Well, the funny thing is, the truth is, it was discovered almost completely by accident.
Let's set the scene. The date is February 23rd, 1940. A day that would, without anyone knowing it at the time, kickstart the entire information age.
There's a scientist at Bell Labs, a guy named Russell Ohl, and he's working with these silicon crystals, trying to make better radar detectors. One day, he's testing this one particular chunk of silicon, and it's just acting weird. It wasn't behaving like any of the others, giving him all sorts of strange, jumpy readings.
So he starts looking closer, and he notices three really odd things. First, whenever he shined a bright light on it, the electric current passing through the slab would suddenly jump way up. Second, he realized that different parts of this same exact crystal were acting in totally opposite ways. And then he saw it, a tiny physical crack or a seam running through the crystal. It turned out that this seam was the boundary line between two regions that had different impurities. He had, completely by accident, stumbled upon the world's very first P N junction.
That one lucky moment at Bell Labs didn't just explain a weird crystal, it basically lit the fuse for a global technological revolution. I mean, just look at this incredible domino effect. Ohl's discovery of the P N junction in 1940, that's step one. A mere 8 years later, his co-workers at Bell Labs used that exact principle to build the first junction transistor, the switch that is the heart of all computers. And then, by 1954, that weird light sensitivity Ohl noticed, that was harnessed to create the first practical solar cell.
From that point on, the P N junction became the essential, fundamental building block. Diodes, LEDs, transistors, the integrated circuits in your phone, every single click, every swipe, every calculation your devices make is happening because trillions of these tiny one-way gates are opening and closing at speeds you can't even imagine.
And that really brings us to a final thought. The P N junction, this thing that completely reshaped human civilization, was an accidental discovery. It really makes you wonder, doesn't it? What's the next fundamental building block, the next accidental discovery that's out there right now, just waiting for someone to shine a light on it?